Hello everyone, and thanks for watching Edupedia World Videos. In this video, we'll talk a little bit about the different kinds of material that exist in the world, specifically conductors and insulators. So, materials are broadly divided based on their electrical conductivity into three categories. The first is conductors, the second is semiconductors. These fall in between conductors, and the third type, which is insulators. Now, you know, broadly speaking, the definition of conductors and insulators. Conductors are those which conduct electricity. Many metals conduct electricity very easily, and they are called good conductors. Then there are materials which do not conduct electricity at all. And they are called insulators, or sometimes they are also called dielectrics. And semiconductors are a very special case of materials. We'll not go into them in detail in this chapter, but they generally behave like insulators at cold temperatures or at the coldest 0 Kelvin, but conduct some electricity as the temperature increases. And the resistance of the semiconductors also lies in between the resistance of conductors and insulators. Right. So we'll talk more about insulators when we reach capacitors, because we'll often insert some insulators inside capacitors to change their behavior. Right now I want to talk to you a little bit about conductors and what their specific properties are. So the general model for conductors is that they have nuclei which are placed at specific lattice positions, and they have maybe 1 or 2 or 3 electrons per each nuclei that are in the outermost shell, and that are just free to move everywhere. So they're not generally confined to any particular nucleus, they're just moving around inside the middle in what is generally called as the electron sea. So the electrons of metals are free to move, and that is why metals are good conductors of electricity, because the moment there is some electric field applied, the electrons immediately respond to the electric field. The nucleus, remember, is stationary, so it cannot respond to the electric field as strongly, and electrons immediately respond to the electric field and thus end up conducting electricity. Right. So what really happens when you apply an electric field to the ideal conductors, and every conductor we'll talk about we'll assume to be an ideal conductor. So let's say we have a rectangular slab of conductor of a conducting material, and it is placed inside an electric field E towards the right. Now the nucleus will be stationary and the electrons will be moving, but generally that doesn't matter for our purposes, because we can always assume an electron moving towards the right is the same as a proton or a positive charge moving towards the left. So whenever I say that positive charges will move from the left towards the right, it actually means that electrons will move from the right towards the left, but those two things are completely equivalent. So initially I'll talk about electrons, but later on I'll just talk about positive charges. Right. So what happens when you apply an electric field? The free electrons, they respond to the electric field. If the electric field is towards the right and electrons have a negative charge, the electrons will move towards the left. So what will end up happening is there will be a layer of negatively charged electrons on the left side of this slab. Because electrons will shift towards the left, there will be a deficit of electrons, and a net positive charge will be created towards the right. Right. So now let's say this electric field has a magnitude of 10 units. So every electron is experiencing an electric field of 10 units towards the right. Right. Now if there's a little bit of charge on these two sides, then they will start applying their own electric field. So these electrons towards the left will apply an electric field towards the left, and these positively charged protons towards the right, or a deficit of electrons in other words, will also apply an electric field towards the left. and those electric fields will add up, and let's say they give a net electric field of 2 units. So any electron here experiences an electric field of 10 units towards the right due to the original electric field present, and it experiences an electric field of 2 units towards the left due to this what is called the induced charges. Remember, this slab is completely electrically neutral, but due to the presence of an electric field, some charges might be induced at some particular surfaces because the inner components of the material respond to the electric field. Now, still any electron is still experiencing a net electric field of 8 units towards the right, 10 minus 2. So they will still again start moving towards the left until this particular charge density towards the left and this charge density towards the right, they will keep on increasing. As long as there is a net electric field towards the right, electrons will move towards the left, or in other words, positive charges will move towards the right, and they will create an opposing electric field. There will come a time, however, when the electric field due to this induced charges will keep increasing until it becomes 10 units as well. At this point, any positive or negative charges inside the material will not feel any electric field at all, because any electric field created by the original field will be negated by the equal and opposite field created by the induced charges. And this process typically takes a very small time, maybe microseconds. So this time is generally assumed to be negligible, and the result which we come up with eventually is that conductors always have E is equal to 0 inside them. Now inside them means inside the actual material. We will come across cases later on when we'll actually make a cavity inside this material. So even though this will all be material, this will be air. And in that case, the situation is slightly different. But for now, we've easily proved that within the material of a conductor, the electric field has to be 0. The net electric field. Because whatever electric field we are applying externally, the electrons and the charges within the material will rearrange themselves accordingly such that the net electric field will be 0 inside the conductor. Right. Now this has some other special properties as well. We've taken this to be a rectangular slab, but actually it could be any piece of conducting material. So if this is some piece of conducting material and we put it within an electric field, then there will be maybe positive charges, negative charges, a whole sequence of randomly induced charges will be created, and those sequences, those patterns will be such that the electric field inside will be 0 everywhere. Now what it also means is, because electric field is 0 and V2 minus V1 is equal to integral of E dot dr, where this is the potential on the surface is the same everywhere, because we could go across any line within the conductor and electric field is 0 everywhere. So not only is the electric field 0 everywhere, conducting surfaces, well, actually the whole conductor in fact, but for us conducting surfaces will be important, are equipotentials. Right. Another important property, the electric field is always perpendicular to the surface. Outside it. Actually, I should say just outside it. For example, if you take this point, the electric field here has to be outside, because if the electric field had a tangential component, then the induced charges at this point would rearrange themselves, and they would keep rearranging themselves until this tangential component vanished. So in equilibrium, the electric field everywhere just outside the surface is perpendicular to the surface, the direction of electric field. It might be inside, it might be outside, but it is always perpendicular to the surface. It does not have any tangential component. Okay. So these are the three basic properties of conductors. Now, sometimes you can actually measure insulators by how much they behave like conductors. So for example, if this is a slab of material and I apply an electric field of 10 units towards the right, that is the inside electric field, and induced charges develop, and if this was a conductor, the induced charges would create an electric field towards the left of 10 units to exactly balance the original field. And this in part happens because conductors have a huge number of electrons, and so they can just keep rearranging without the electrons running out. But insulators do not have a large number of free conductors or free electrons. So what they might do sometimes is there will still be induced charges, but the charges will not be enough so as to cancel the original electric field. So for example, some weakly insulating materials might just be able to create 5 units of electric field in the opposite direction. Some strongly insulating materials which cannot conduct electricity at all might just create 1 unit. And materials which absolutely cannot conduct at all, which are the perfect insulators, might create 0.001 units of an electric field towards the left. So we'll see this later when we come to capacitors, but this is an interesting way to measure how much conducting or how insulating a material is, apart from obviously its original resistance, which in turn is a measure of how much conducting it does. And this particular thing is related to what is called a dielectric constant, which we'll see in capacitors. But if there's a conductor, then there is no shortage of free charges, and so this electric field will be 10 newtons in the opposite direction to completely negate it. There is one small final concept which I'd like to deal with, and this I didn't introduce in the last video because sometimes it confuses some students, because when they're new to Gauss law this seems confusing. So I'll just explain it now in regards to Gauss law. So one thing we saw previously was that if I have an infinitely long plane sheet, a surface charge density sigma, then what I did was I created a Gaussian pillbox. This should be cuboidal, but that actually doesn't matter. It could be cylindrical as well, as long as it's a pillbox. These two areas are what matter. And we assume that both of them will have the same magnitude of electric field in the opposite direction. And so we got E into A, twice of that because twice is the flux, is equal to sigma A by epsilon naught. And from that we got E is equal to sigma by 2 epsilon naught. Right, and this is the original result. This is the completely accurate result. If you are confused by me using a cylinder, you can assume me using a cuboid. That doesn't really make a difference. I understand now it might be confusing because I took cylindrical symmetry and spherical and planar, but this is planar symmetry. This is not cylindrical symmetry. So E is equal to 2 by sigma by 2 epsilon naught is the standard result. And that result is true when we have a plane sheet of charge density sigma, and that's it. Nothing else. But what if we were to have a big conducting material, let's say a big rectangular slab of conducting material, and this particular side had a charge density of sigma? What would the electric field be then just outside? In the previous case, when we just had a single sheet, it was sigma by 2 epsilon naught, remember, because we took both sides, right? So now what we'll do is we'll make a similar Gaussian surface, a cuboidal surface, and if we say the electric field here is E and this area is A, E into A plus 0 into A is equal to sigma A by epsilon naught, because here the electric field is E, but if this is the conducting material, then the electric field here is 0. So this will be 0. And that gives me E is equal to sigma by epsilon naught. And this is something which generally confuses students, that if you have a single sheet of charge density sigma, then what is the electric field outside it? Is it sigma by 2 epsilon naught or sigma by epsilon naught? The answer is the electric field due to a single sheet will always be sigma by 2 epsilon naught. But this is not a single sheet, is it? Because there are two ways you can look at this. One, you can just purely use Gauss law and see that the electric field here has to be sigma by epsilon naught. Or another way you can look at it is the way I like to look at it, which is the electric field due to a single sheet has to be sigma by 2 epsilon naught. But if this is a single sheet, then here it's sigma by 2 epsilon naught, and here it's sigma by 2 epsilon naught. But here it's only on one side. On the other side, electric field is not sigma by 2 epsilon naught, it's actually 0. So what's happening there? What must happen is there must be some other charges on this other end which do something to make the electric field on the left 0. Right? So if the electric field is sigma by 2 epsilon naught here towards the left, right, this in this particular case will be positive actually, then there must be another set of charges on the other end or somewhere else which create an extra electric field of sigma by 2 epsilon naught towards the right within the conductor, such that the electric field within that conductor is 0. And of course, if this particular sheet of charge has a field of sigma by 2 epsilon naught towards the right within the conductor, it also has a field of sigma by 2 epsilon naught towards the right outside the conductor, and these two sheets together give an electric field of sigma by epsilon naught, which is the electric field at this side. So the electric field just outside a conductor will be sigma by epsilon naught, but that is not the electric field by this particular charge sheet alone. It is by this plus other combinations of materials. But remember, these two cases are different. If you have a single sheet in which both sides can have electric field, then it is sigma by 2 epsilon naught. But if by some miracle you actually make one side of this have an electric field equal to 0 by putting it in the material of the conductor, then whatever changes you made to make the electric field 0 on the left, the same changes would change the electric field on the right to make it sigma by epsilon naught again. So for a single conductor in which you have electric field 0 on one side, it is sigma by epsilon naught, but a single plane sheet will always have an electric field on sigma by 2 epsilon naught on either sides. Think about this again. I don't want you to be confused by this because we'll use this again and again when we reach capacitors. That will be the next video. Thank you.